prediction of phase structure which is not known experimentally. You will not find it in any experimental databases. And I was very anxious to see what experimentalists will do because I knew that they are working on it. I actually stimulated them to work on it. And for 2 years, I was shivering at night, with cold sweating. Oh, what if they find something else? Well, they found the same stuff. So I can sleep well now. No, I cannot sleep well because I'm jet lagged. Anyway, I just arrived with an 11-hour jet lag, and I'm a little bit shaky on my leg. Anyway, for magnesium carbonate, the situation is much more complicated. We have a whole bunch, about a dozen structures with extremely similar enthalpies in a wide pressure range. And experimentalists actually turn out to produce irreproducible results. 2 experiments exist, and their diffraction patterns are incompatible, probably because of this existence of many competitive metastable structures. Okay, so I'll skip that. Anyway, the picture that we draw for carbon in the Earth's mantle is highly consistent with experiments, and we have made one funny prediction, which I will describe in a minute. So in parallite regions, or in paralytic mantle, where environment is reducing, we find diamond and cementite to be dominant, except the top of the lower mantle, where we predict magnesium carbonate to be dominant. In subducted slab, it's carbonates, first magnesium carbonate, and then in the D double prime layer, calcium carbonate pops up. The unusual things that so this is consistent with observational evidence, which finds diamond inclusions in mantle rocks and also some carbonates. What is unusual is that we predict that cementite should be a very important host of carbon. And that was a pure prediction, which again made me a little bit scared to make. But then my colleague Adrian Jones from London contacted me and said that he finds actually lots of cementite in diamond inclusions. So that probably is also correct. Okay, we find that CO2 can be produced only in the D double prime layer, and that can have also implications for viscosity and partial melting and so on of mantle rocks. All right, so we have also made some recent developments of the methods. For instance, we have discovered a new function which, when you apply it to a crystal, can immediately visualize for you how well atoms sit. So this is a hypothetical structure of SiO2. The function is called a degree of order, or local order. Red atoms have high values of order, blue atoms have low values of order. And so immediately this plots for you the region of a defect. Yeah? So if you want to change something in the structure, mutate something in the structure, you know where to start. These regions must be mutated before these regions get shuffled around. And that these kinds of developments actually improve the speed of calculations by a further factor of between 2 and 5. So now we can study relatively large systems. We have done a blind test for the first time for inorganic crystals. We have done a blind test of different structure prediction methods. I have invited all groups that develop or use different methodologies, and 3 groups agreed to participate. People using random sampling, people using simulated annealing, and us. We have done 4 tests where none of the groups actually knew the solution. We took very challenging, more or less random compositions, very complicated chemical formulae where no experiments exist and nobody did calculations before. And the task was, who finds the lowest energy using exactly the same force fields or density functions and so on. So 4 tests were conducted. Random sampling lost to all other methods in all 4 tests. So as I mentioned to you before, simulated annealing, to my great surprise, won in 1 of the tests. And in 3 tests, we won. And the effort associated with our method was several times smaller than with random sampling or with simulated annealing. So I think it just shows you that we are on the right track. Okay, here is just an illustration of how the energy evolves in an evolutionary simulation and in simulated annealing. One of the things that you can notice is that in simulated annealing, the final result has a very wide distribution of energies. So you have to repeat many, many times simulation with simulated annealing in order to be sure that you are not doing some trash. in evolutionary simulations, final energies are very highly reproducible. So that's another advantage. Okay, just a few illustrations of what we are also doing. Boron. Boron is the most complicated element known to humans. Everybody who worked on boron among great scientists has done great errors. We are not great scientists, so we have got it correctly. When it was discovered by Gay Lussac and Davy, greatest chemists of the 19th century, later it actually turned out that what they dealt with was not boron, but a compound containing not more than 60 or even 50% of boron. So it's like you look at sodium chloride and say this is sodium. This is just as good, I guess, that they had. The person who proved them wrong, Moissan, another great chemist, thought he had pure boron. Actually, he didn't. And in fact, pure boron was probably synthesized for the first time in 1957 at Cornell. And until 2007, it was not known which forms of boron are stable at ambient conditions, which ones are pure and which ones are not, and that was a full mess. Chen and Solozhenko experimentally synthesized this phase, a new phase in 2004. In 2006, they approached me to solve the structure, which was solved. It was found that this is a super hard material, one of the hardest known materials, about fifth or sixth hardest known material. And it has a very peculiar structure where there is a strong charge separation between boron-12 icosahedra, which attract all the low energy electrons, the bottom of the valence band, and the boron-boron pairs, which concentrate the top of the valence band and bottom of the conduction band. In other words, holes in the electronic distribution. Okay, I will not tell you more. Basically, this structure is similar to the structures of compounds such as boron phosphide, and these two boron sublattices play roles of basically different elements. You can say this is a partially ionic compound of boron with boron. One of the consequences is that while normal phases of boron metallize at about 1.5 megabar, this phase of boron shows very little pressure dependence of the band gap and does not metallize. Okay, you could ask me what hell this has to do with the Earth, yeah, and with planetary materials. I think this phenomena of desymmetrization and charge disproportionation are one of the new common phenomena that people increasingly frequently find under pressure. And if we want to understand, for instance, the behavior of hydrogen in planetary interiors, it may be crucial to understand phenomena like that. And okay, and a more relevant result, although seemingly less relevant result, is on sodium. Sodium displays one phenomenon that may turn out to be crucial for understanding interiors of giant planets. Okay, sodium is an element which normally is a free electron metal, very well described by the free electron model, believed to be simple S metal, until 2002, when people discovered a host-guest structure, which is actually non-periodic, and which actually is a quasi-one-dimensional metal at pressures of about 1.2, 1.3 million atmospheres. Then they found a very deep minimum on the melting curve. And a further surprise came with our prediction that sodium at pressures of about 2 megabars will become an insulator. Not only an insulator, but a transparent insulator, a very wide gap insulator. So the idea was that if you squeeze sodium, normally it's a white, silvery shiny metal. You squeeze it, and then it will become, at pressure of 2 megabar, red, transparent insulator like ruby. So it's like alchemy, magic. You squeeze something that looks like aluminum, and bang, it suddenly looks like ruby. We sent our paper to Nature. It was immediately returned to us with a comment that we cannot publish all crazy predictions and go sort yourself out. And we sorted ourselves out by contacting an experimentalist, Yeremets, confessing our sins to him, saying that we have a prediction which nobody believes. Can you look into it? And he, a couple of weeks later, he sent me the photographs. Sodium at 1.1 megabar, still silvery, shiny metal. At 1.6 megabars, it's already non-reflecting, black, like coal. And at 2 megabar, transparent red, just as prescribed by theory. And then the paper immediately was published in Nature. And nobody can say that we're making crazy predictions. Nobody. Okay, why am I saying that this stuff is important for planets? Because what is happening here is happening entirely because of pressure. Valence electrons at low pressure orbit the atom of sodium at relatively long distance. They are repelled by the core. They cannot they cannot have high density inside the core region. So they get far from the core region. When you squeeze the atoms of sodium on top of each other, core regions overlap, and valence electrons have no other choice than to occupy places which are far from nuclei, than to occupy some corners. Valence electrons are cornered into some small pockets of space. And then they cannot tunnel from place to place. They are locked. They are locked and localized, and conductivity collapses. That's the essence of the metal insulator transition in this case. Okay, we can expect a whole bunch of new phenomena from this, and this can be described as a compound. Again, if you like, an ionic compound made of ionic cores, positively charged, and negatively charged electron density maxima that serve the role of anions. Such situation has been described for a long time in chemistry by the word electrite. Like fluoride, chloride are salts with chlorine, fluorine, and this is a salt with electron, yeah? Electrite. And we can actually expect such phenomena inside giant planets or perhaps even some stars like white dwarfs, where atoms are strongly squeezed. And such insulating states or badly conducting states could occur there and could affect, for instance, magnetic fields. Okay, the last thing I want, the last topic I want to describe is methane. Methane in the interiors of Uranus and Neptune. So we can expect that there will be some really exotic states of matter inside giant planets. And one of the relevant questions here is the generation of heat inside Neptune. Once luminosity of Neptune was measured, it became immediately clear that it is much greater than expected from simple planetological models. And Neptune must generate tremendous heat inside its interior. The question is that nobody knows from where this heat comes. There are no radioactive elements there, no uranium, no thorium. It's just a mixture of lousy molecules, water, methane, and ammonia. Nothing radioactive here whatsoever. Well, the only hypothesis that people have come up with was the breakdown of methane into diamond and hydrogen. And diamond is dense, it falls in the interior of the planet, and the gravitational energy transforms into the heat. That was the explanation. So it's rather exotic. Planet being heated by falling diamonds, not even burning diamonds, but by falling huge amounts of diamonds. This was addressed by a number of experiments which were mutually contradictory and ab initio molecular dynamics calculations. Calculations were state of the art at that time. The trouble with molecular dynamics is that it is not really a very suitable method for observing chemical reactions because you get trapped into local minima, into metastable products, and you can never be sure in what you actually generate. What we have done was to address it with our evolutionary method. We have generated the phase diagram of methane, and we found that indeed methane disproportionates into hydrogen and hydrocarbons. First ethane, then butane. So something close to gasoline. Hey, we can go to Neptune to mine for gasoline. And then diamond. And then you can go and mine for diamond on Neptune. What is peculiar here is that diamond is only formed because of quantum zero-point vibrations. If you disregard the effect of quantum zero-point vibrations, you will not have diamond stable on the zero temperature isotherm. So there is quite a lot of interest in physics. We have further extended our method to deal with, so I mentioned to you nanoparticles, I mentioned to you surfaces. This is another aspect, variable compositions. So here we no longer specify the chemical formula. We just specify the names of atoms. For instance, magnesium, silicon, oxygen. And then this thing has to figure out